In this presentation, I'm going to go over density, both what it is and how to calculate it, as well as one situation where we can use it to predict something that would happen in real life. So, quick overview of the contents. First, we'll talk about what density is, both on the macro scale as we see it, and on the micro scale as we interpret it as far as atoms and such go. We'll then talk about how we measure density in the different parts. We'll get into some calculations, and then we'll specifically talk about buoyancy. So first, what is density? Density, by definition, is the amount of matter within a given space. But there's really two vocab words I want to put in here. When we say matter, we're specifically talking about mass, how much stuff is in a space. And this is analogous, but not quite the same as weight. And it's that amount of mass within a volume, so how much space something takes up. For instance, let's say we're building an airplane. When we're designing an airplane, would we want to use a heavy material or a light material? You might think back to those old gliders you used maybe in, say, elementary or middle school. We might think that we want a light material to make a plane. In reality, we're really thinking about the density. Yes, we want a light material, but it still has to take up some amount of space. So we really want something that is light for how much space it takes up. For instance, let's look at two different substances. On the left, we'll see balsa wood, that super light wood used in planes. It has a density of around 0.475 grams, that's the mass, for every 1 cubic centimeter, that's the space it takes up. Compare that to something like steel, which has a density of 7.85 grams, that's how much it weighs, per every cubic centimeter. Really, we're seeing that steel is almost 20 times as dense as balsa wood. In the same amount of space, steel would weigh about 20 times as more. Now, what does this actually look like on an atomic scale? If we were to take a small section of balsa wood and the same size section of steel, we would see that the atoms in balsa wood on the left here are more spread out. They're also going to be different elements, which we'll get to in a later unit, but right now it's okay to think of them as just more spread out. Whereas in steel on the right, those atoms are really packed together. You'll see there are some even smaller atoms kind of packed in between the bigger ones. Overall, this makes a lot more stuff, a lot more mass or matter in a given space. So we can really think of density as partly due to how many atoms there are within a similarly sized space. So how do we actually measure density? Well, it's pretty simple. The first thing to measure mass, it's similar to weight. So just like we might step on a scale or use a scale in the kitchen, mass, we're going to use a balance to measure it. We'll talk about that a little bit more on the next slide. Volume is a little bit different. Again, it's how much space that object takes up. We have a couple of different units we're going to be dealing with here, centimeters cubed, milliliters, or liters, and we'll talk more about this later, but know that centimeters cubed are the same thing as milliliters. If we have 1 centimeter cubed, we have a milliliter, 1 milliliter. Now, how we might measure volume, one way is with a ruler. We can use measurements along with some geometric equations to calculate volume. We might also use something called the water displacement method. This is something you'll see in the lab for this unit. And you could use 3D scanners. That's kind of the new tech way of doing things. I'll talk about that briefly in a couple slides. So like I said with measuring mass, really mass is how much of a material there is. It's how many atoms. And for us, it's going to be weight. So if we say wanted to measure the mass of this piece of balsa wood, we would just put it on a scale. And it's like putting those atoms directly on the scale. They're basically just a big pile of atoms that we're saying how much do they weigh. So mass is pretty simple to measure. Volume, our first measurement for how much space that object takes up, I'm going to call that direct measurement. And that's where, for say a rectangular prism like this balsa wood, I would take the length, width, and height of this piece of wood, or really just the distance of each side, would do that in centimeters. And for anything that is cubic or a rectangular prism, the process is pretty easy. You just multiply the length of each side together. So if I take 2.1 times 3.7 times 0.7, centimeters times centimeters times centimeters, I would get a final answer of 5.4 centimeters cubed. And that's how much space that block takes up. For cubes, it's pretty simple. For other solids, you'll see there are a little bit more difficult equations. It's never too crazy, but the farther you get from cube, the harder it is to use a ruler. That's why, for this, not the direct measurement, but our second method, it's going to be called water displacement. And this makes our jobs a little bit easier. Really, what we do in chemistry is we first measure the water level in a graduated cylinder with nothing in it. That's what you can see on the left here. We would then put our object in the graduated cylinder. On the right, you can see that we've put in this, looks like a bolt here. We've put that in the graduated cylinder. You can see that the water level rose. We would measure the new water level, and then we would calculate the difference in water levels. And that would correspond to the volume of our bolt here. So really, it's just saying the water rises by the same volume that that bolt takes up. It has nothing to do with mass of the bolt, how much it weighs. It's all about how much space it takes up. And for our third measurement, for just as a brief aside, you could use a 3D scanner to measure the volume of some kind of component. This would take some kind of, say, calibration, and it can be a little finicky, but this is kind of new tech. You put an object on a rotating plate, or you can actually have the object rotate around the sensor, and the sensor tells you how much volume it takes up. Little more tech, little more expensive, can be harder to use up front, but at the end of the day, it's a fairly simple technology to use. So how can we calculate density? Well, really, we only need those two parts, mass and volume, because density is the relationship of how much mass there is in a given space. So you see density just equals mass divided by volume. And we could abbreviate that as D equals M over V. So if I go back to my balsa wood example, if I measured this balsa wood and got a volume of 5.4 centimeters cubed, and let's say I put it on a balance and it was 2.67 grams, I could just plug those into my density equation, 2.67 grams over 5.4 centimeters cubed. I could do that division, getting 0.494 grams per centimeter cubed. Notice the units from the second step match the units in the third step. And we want to be careful about significant figures. Since our volume only has two significant figures and our mass has three, our answer should really be limited to two significant figures. Also notice that I changed centimeters cubed to milliliters. You don't have to do this, but I want to point out again that centimeters cubed are equivalent to milliliters. You can use them interchangeably. 1 centimeter cubed is equal to 1 milliliter. And that's really it for calculating density. You have to find the mass, find the volume, and then divide them. Now let's talk briefly about buoyancy. What is buoyancy? Buoyancy is the tendency for something to float, usually in water, but it really could be any liquid. And let's take, for an example, this kind of block in a beaker of water. Buoyancy is really the balancing out of how much the object weighs versus what is the force of the water pushing up on the object. It's getting a little bit into the physics of things. We're going to use this as an example of how to use density to calculate that buoyant force. As an example, let's take a boat in water. Really, what we know is that whichever weighs more will sink, the boat or the amount of water it displaces. Now, what do I mean when I say the amount of water it displaces? Imagine a boat in a pool of water. The space the boat takes up will be equal to the space of water that would be in the pool otherwise. So if I take my boat and I say, for instance, know that its mass is 2,500 grams, and I know that its volume is 3,500 milliliters, which I could get through mathematical calculations and measurements, I actually know something about this displaced water. It would have the same shape as the boat because the boat is taking up that space. So even though I don't know the mass of that water yet, I do know the space that it takes up. It's equal to the space of the boat. So how can I calculate this mass of water? Well, let's take what we know and that one thing we're trying to find here and list them. Remember that whichever weighs more will sink, the boat or the amount of water it displaces. We know density equals mass times volume, but if we do a little bit of algebraic manipulation, we can find that mass is equal to density times volume. And I'll abbreviate that to m equals d times v. And really, in this situation, we're still trying to find that mass of water. We know that the mass of water equals the density of water times the volume of water we're talking about. And in this case, that's the displaced water from the boat. So I'll use m equals d times v. I'll plug in my density of water here, 1.00 grams per milliliter, and I'll multiply it by the volume of water that's being displaced by the boat, 3,500 milliliters. Now this problem's kind of silly. It's just 3,500 milliliters times 1. But notice that the units of milliliters here cancel. So we're left with the mass of water, 3,500 grams. We know that the boat, 2,500 grams, weighs less than the water. Saying that again here, the boat is less than the water. Therefore, the boat is going to float. Essentially, that water is more dense or dense enough that it will sink below the boat because it will weigh more than the boat. If we changed liquids and changed this density, that very well may not be the case. And that's what you'll practice in this section's practice.